Welcome! Today we'll solve a challenging problem involving trigonometric functions and implicit differentiation. Let's start by looking at our problem. We're given that sine of x equals 2t divided by 1 plus t squared, and tangent of y equals 2t divided by 1 minus t squared. We need to find dy dx. Let's solve this step by step. First, let's focus on the equation for sine of x. We can take the inverse sine of both sides to solve for x. This gives us x equals the inverse sine of 2t over 1 plus t squared. Interestingly, this can be simplified to 2 inverse tangent of t. Now that we have x in terms of t, we can find dx dt. Using the chain rule and the derivative of inverse tangent, dx dt equals 2 over 1 plus t squared. Let's do the same thing for y. Starting with tangent of y equals 2t over 1 minus t squared, we can take the inverse tangent of both sides. This gives us y equals inverse tangent of 2t over 1 minus t squared, which also simplifies to 2 inverse tangent of t. Just like before, we can find dy dt. Using the same derivative rule for inverse tangent, dy dt also equals 2 over 1 plus t squared. Now we can find dy dx using the chain rule. We know that dy dx equals dy dt divided by dx dt. When we substitute our expressions, we get 2 over 1 plus t squared divided by 2 over 1 plus t squared, which simplifies to 1. Therefore, we found that dy dx equals 1. This means that y is changing at exactly the same rate as x. This is a fascinating result that shows how parametric equations can sometimes lead to surprisingly simple derivatives, even when the original equations look quite complicated.